Welcome to Wikispeedia. My name is Jack.
Macy.
David.
I'm Rohan.
So what are the goals of our Wikispeedia project? Well, first of all, let's talk about what Wikispeedia even is. So Wikispeedia is a community-created game that you can play on wikipedia.com. And so how you play is you start on some article and you must navigate to some other article using only links on Wikipedia pages. So for example, if I want to start on Hayabusa 2 and end at Tanegashima Island, I would navigate through and kind of peruse through the Hayabusa 2 Wikipedia article. And if I found a link that I thought might get me closer to my destination, I would click on it. So here I click on JAXA, and then I find actually what I'm looking for, and then I'm done.
So Wikispeedia as a graph, our graph is a directed graph, and each vertex would represent the article of the Wikipedia right here, which is a snippet of our data set, and edges would represent the links from one article to another, which is in this picture right here. And it would have the start vertex on the left, and then the right side would be the destination vertex. And our graph isn't necessarily like one big graph because there might be like vertices that aren't connected.
So getting a little more into the actual data set we're using, it's titled Wikispeedia Navigation Paths from the Stanford SNAP datasets. And so it's not actually the entire Wikipedia graph. It is just a condensed version of around 4,500 articles and their associated links. And the formatting, as Macy mentioned, are two TSV files, one for the articles and one for the links. So our development process. So we used a class structure like so. For each of our three algorithms, which are BFS, Dijkstra, and Landmarks path, they implemented a graph path algorithm interface, which is described below. This makes it really easy for testing, Git development, and debugging. All the calculations are done in the constructor. Guess ending point, get starting point, and get path can all be done in constant time.
So our traversal method was breadth first search traversal method, and we decided to use this because the main goal of Wikispeedia is to find the shortest path from the starting vertex and to the end. And what BFS would do is it would traverse all the vertices of the graph, and then see if the destination vertex exists. And this was done by using the queue. And then the unordered map is to keep track of the visited vertices and then the edges. And these vertices are either labeled visited, unvisited, or cross, or discovery, just like the ones from the lecture. And once it's finished, we find the shortest path when the weight is 1 from the starting vertex to the destination vertex. And then the pictures right here shows how this is done. And one of the problems that we encountered in the beginning was that when we were printing the path, like a lot of the vertices would just repeat itself. And this was because since the path that we're printing out is actually all the paths taken from the starting to the end, it would actually print out all the edges. And when printing, we had it so that it would print the start vertex of the edge and not the end. So at the end, you see that it only ends with like an arrow and not actually the 10th century article that we were actually trying to find. And then the second problem was that it kind of ties in with the first one, where we were kind of confused if we should actually return all the edges that was visited when BFS was called, or if we should just print the actual path taken from the first, like the starting to the destination. And we actually just decided to actually do like both ways, where we would print out all the vertices. And then after that, we would print just the shortest path taken when the BFS is done. We would search for the shortest path, and then we would print that too.
So for our shortest path, we decided to use Dijkstra's algorithm. And as we know in Dijkstra's algorithm, we have a start node, and it calculates the shortest distance to every other node. In this algorithm, we use a priority queue to decide which node is up next, specifically the smallest pathway up to that point. In our implementation, we decided that each edge weight would have 1. So some of the issues we had were the designs for our priority queue. We decided to use the struct as a comparator in the priority queue, and that's how it would decide which vertex would be up next. We had to add a get weight and set weight in the vertex class. In addition, the vertex weight was not holding between the for loops designed in the original Dijkstra's algorithm. So we decided to condense the two for loops into one for loop.
And our final algorithm is landmark path, which after learning about it was a little more simple than we thought. So we used the Coursera course and we figured out that it's just two shortest path calls from A to B and then from B to C. We looked into an optimization mentioned in the Coursera course, although our graph was not undirected, so we couldn't do that. BFS is actually an algorithm we could have used over Dijkstra for the implementation of landmark path, although we wanted to use Dijkstra just to account for any future case where the edges are weighted, and we'll mention a few of those future cases at the end. So a few of the problems we had with landmark path were that a landmark path has its own funky edge cases that you don't really expect when you're just combining two shortest path calls that don't have the same edge cases. So for example, if you're connecting A to B, which are connected and they're in some subgraph, and then to C, which is not in the same subgraph, you have to account for that.
So per the project requirements, we were mandated to test our project code to make sure that there weren't any logical errors in our project. Now, the two main reasons to actually test in this project is to check for edge cases to ensure that nothing in this project will crash in the case that we do encounter an edge case. And the other reason to check is if the expected output behavior actually does match the actual expected output behavior upon inputting certain values and parameters. So in this, we have an example right here of a sample test case that involves vertex graphs and edge graphs being read into graph G. And upon inputting these values into the function that we're testing for, such as landmark, we will require that the starting point be equal to V1, the middle point be equal to V2, and the ending point be equal to V3. So second to last line, we have a vector of an edge. We expect it to be V1, V2, V2, V3. And in the end, we are requiring that the expected output be equal to expected. So the problems that we ran into for testing was that it's tedious to test these functions out because there's so many expected behaviors that we can like expect and choose from. Like we had a total of 33 test cases. That was quite a lot. And each test case, it can look significantly different by a substantial amount. So copying and pasting and modifying each test case, it's not always advantageous.
So as for our actual deliverable, or the executable that we created is this Wikispeedia tool. So it's a command line program that loads in the Wikipedia dataset, and then you can run each algorithm from this command line interface. And it also has a few extra features that we'll show off in our demo here. So now I can specify custom data. I'm going to say no so that we can load the snap data set. And now if I run BFS, it asks me for an article to find. So if I am looking for Airbus, it'll show me all the articles that it visited in the traversal. It also shows me how many were visited and how many were not visited, how many edges were visited, how many cross edges, and how many discovery edges. You might notice that there's a discrepancy between discovery edges and visited vertices, and that's because there are some vertices that are not connected. And then at the very bottom, you can see path to vertex. So beginning at whatever starting point it began at, it'll show you the shortest path there. For the actual shortest path, now we can go maybe from Airbus to Canada, and then it'll calculate the shortest path there. And then finally landmark path. So say we're going to Canada, and then we're going to China, and then back to America. Oh no, that article doesn't exist. So that's one thing that we built in, was that if the article doesn't exist, we'll ask you for a new one. So in this case, we'll just say the ocean. And then there it gives you the path through China from Canada to the ocean. So a few concluding thoughts. Dijkstra's algorithm for the shortest path would be a little bit more effective if there was more descriptions. For example, if you were factoring in load time due to number of images and the document length. The data set shape is fairly similar to a B tree, just because there are so many edges compared to the amount of vertices. So this means that it's a very wide graph, and BFS is not very maintainable as the data grows larger. So if we were using the entire Wikipedia site as opposed to this condensed version, then we would probably switch to DFS. And then finally, we can extrapolate some strategies for a human playing a Wikispedia game, given that the distance between any two articles is always very small. In our testing, it's been around 4 or 5 max. It makes sense to spend that extra time looking through every article or every link in the article rather than clicking the first one that seems right, just that you can try and gain that actual shortest path. And then another strategy is navigating to a page that has a lot of links on it, because that'll give you a better chance of finding your ending article. Thank you.